Hey guys, welcome back. So finally, after all these videos that you've gone through, we're now here at experiment 1, and that is our simple audio amplifier. So let me kind of step out of frame here, and voila. So you remember how we were showing you all the the resistors and everything like that, and then your circuits, and showing you the linear equivalents. There's no real linear equivalent of this, but this is how our circuit looks.
Right.
And Aspen and I, we both know, you're like, oh my God, this looks so complicated. But oh my God, it's really not. It's only like 11 overall components that's actually going to go on board your bot or on board your breadboard.
Right.
So you've got these 5 resistors, you've got 4 capacitors, and you've got 2 BJTs. And you say BJTs, well, what's that? Well, BJTs, the meaning of the acronym is bipolar junction transistors. And Aspen here has got a great way of explaining it to you real quick. So we're going to let him explain very briefly and give you the overview of what BJTs are and how they function.
Right. So the key word for BJT, or bipolar transistor, or junction transistor, is biasing. Okay. Simply to put it, it's 2 things really. It's electrons, which I'm sure you guys learn in science or whatnot. Okay. The particles with a negative charge, right? And holes, okay, where electrons aren't, right? As you can see here, we have arrows drawn actually going down out of the BJT component, right? That's signaling that's our current flow direction, right? So it's really electrons and holes passing through the BJT. Pretty much make sure that we have what's called a forward bias, which means that that the current is flowing in a certain direction to make sure that the component is on and working. Okay. So simply put it, it's forcing electrons to flow in a certain direction, based off of the amount or value of voltage that's going into the component. Okay. And definitely we'll get to see how it actually looks on a breadboard, because it doesn't look exactly like that in real life. Okay, it looks a little different. That's just the symbol we use in circuitry when we draw it out of a transistor. Okay.
So we've got 3 parts to a transistor. We've got the collector, which kind of sounds like what it does.
Right.
You have the base, and then you have the emitter. There's many different ways you can hook these things up, but basically what we're going to show is we have what's known as a PNP transistor, and that means that it is a positively biased transistor.
Right.
You have a PNP and you have an NPN. Well, right here we're dealing with PNPs for a reason. We have our 12 volts DC, and we use DC to bias the circuit for a reason, because that's going to give us our conditions, because these things have 3 different operating ranges. They have the not functioning, the off condition essentially.
Right.
Then you have saturation, which we'll explain, and then you have the middle condition, which is the you know what?
In between on saturation.
Yeah, it's in between off and saturation.
Right.
And this is your area where the transistor works really, really well. We just had that written down. We just forgot about it. However, it'll be written in your lab manual of what this condition is. And we're going to go ahead and we're going to show you, just real quick, we're going to step over here. We're going to show you what these 3 conditions essentially are. So you have, this is where your collector's at. This is going to be where your base is at, and then your emitter's right here. Well, we're going to break each one of those down into, well, you're going to have a different voltage here than you have here than you have here. And there's going to be some theoretical values that we're going to use, some theoretical assumed values. We're going to theoretically assume, and this is pretty consistent across the board, that the voltage difference between these 2 and a PNP is 0.7 volts. So that's just an assumption. it gives you the theoretical values versus your actual values, because we all know that our theoretical values are not going to match our actual values.
Right.
That's
never.
yeah. If it does, you have discovered a unicorn. I kid you not.
Right.
Like, patent that thing.
Please.
So essentially, because we have different voltages for each one, I'm going to write it down here. We have VC, voltage at your collector, VB, which is your voltage at your base, and your VE, which is your voltage at your emitter. I don't know if you guys can see that. Maybe we need to write it a little bit bigger. I don't know. But obviously, in your off condition, what's going to happen is your VB is going to be greater, and I drew that wrong. My apologies.
There we go.
Your VB is going to be greater than your VC. And it doesn't matter what's at your VE, because if your VB is greater than your VC, nothing's going to happen.
Right.
Maybe it's transient mode. Maybe that's what I'm thinking. Well, in your normal operating range, what's going to happen is your VC, this is for PNPs, your VC is going to be bigger than your VB, and your VB will be bigger than your VE. And this is your optimal operating range right here. When your voltage at your collector is bigger than your voltage at your base, which is bigger than your voltage at your emitter, you
Right.
are good to go.
And you can think of it like this, if that's so confusing. In simply terms put as well, your voltage is what pushes your current through your circuit, right? So obviously, to get our current to go direction, our overall current to go directly down this way direction, we obviously need our voltages here and here. That'll be greater than one another, so that way it's ultimately pushing the current down, right, into this direction.
And yeah, that works.
Right.
I mean, that works great. So our next one is saturation. And where saturation is, yeah, it'll work in saturation, but we don't always want it to be saturated. And that's where your VC is going to equal your VB, but your VB is still going to be greater than your VE by at least 0.7 volts. And again, that's just a basic assumption. Once you start really messing with BJTs, you're going to find out, my God, there are a lot of BJTs out there, and this 0.7's not actually going to always be consistent once you actually get down into the hardware of it.
Right.
But at least for theory, this works out great.
Of course.
And then we come to your currents. Your currents are going to be different.
Exactly.
In fact, Aspen, if you want to run them through their currents real quick.
Yeah, no, definitely. So current at your base, if we're starting at the base of our BJT, we'll identify as I sub B, okay, current at the base, okay. It's just going to be pretty small, okay. And of course our current through our collector, the I sub C, and then through the emitter is I sub E, as Brandon finds other places to write it. There you go. And definitely, with these three currents, you definitely are going to want certain currents to be greater value than other currents. So that way, again, we ultimately have our final current going through downward towards through our emitter, right? So our emitter current is actually pretty simple. Our emitter current is actually just our base current plus our collector current. As it makes sense here, you can write that down for me, Brandon. Thank you. Our emitter current is the resultant of our collector current and our base current going through and actually combining in our BJT. Okay, so pretty easy. So as you can see here, right here, pretty much what's going on is that our current here, our current here are meeting. Okay, they're meeting in this component and just being outputted here. Okay, and that's why we need our voltages to be what Brandon said earlier, the way that they need to be, so that way this actually happens. Okay. Um, so also another variable, which that's endless in algebra. Another variable that we'll talk about soon enough is beta. Okay, and that's the gamma. Sorry, that's the Greek letter for B essentially. Beta is actually the current gain in our transistor, our BJT transistor. Okay, and actually you can find current. You can find our collector, our
You can find
the collector
current and emitter current,
right, with
as long as you have IB and beta.
Right. In this case, our beta is actually a known variable, a known value of 100. Okay, for these BJTs, that can also vary as well. But for our sake, beta is 100. So the actual formula for that, so for our collector current is just simply beta times the current value in our base, and then of course our emitter current is actually beta plus 1 times our base current. Okay, which is right there. Our base current times beta plus 1. Okay.
So again, simple algebra, if you remember. So since IC equals this, so then we have our current IB here. So then this is IB beta, or IB times beta plus IB. So we take out our common factor here, which is IB. So then we're left with IE is equal to IB times beta plus 1.
Right.
And again, that's a simple theory assumption. Beta changes a lot. We've messed with beta of 100. We've messed with beta of 150. We've messed with beta of 75. And it's going to get you really close to what you're expecting of your circuit. You may be a little off, but that's fine. And all of this is for what's called your large signal. And your large signal is in relation to your DC component. Your small signal is going to be in relation to your AC component over here. I know it may be a little bit hard to see, but this right here is our power source on this side, which in this case is going to be our function generator, outputting a frequency sine wave for what's going on here.
Right.
So we're going to wipe this out real quick. We're going to try to wipe this out without wiping out the circuit.
All right, there you go.
Wish me luck. And again, a lot of this, the theory behind it, is going to be in your lab manual, so we're really not going to go into a whole lot of detail, but we want you to understand that, we kind of want you to grasp some of the real overall broad stroke basics here. To understand what we're doing and to not be flipped out by what you're seeing right here. Okay, so real quick, all of our green squares that you see right here, this is where one or two or more components are going to be connecting in the same space. So this is where our nodes are at. So right here we've already explained. We've got two BJTs, we have some resistors, and we have capacitors. BJTs are polarity sensitive, which meaning that wherever you hook them up, depending on which type you use, you have to have a positive, a negative source, or positive and then ground. They are sensitive and they will behave differently if you hook them up incorrectly, or may not behave at all, or you may burn something up. Resistors and capacitors, not polarity sensitive. So, right. So this is pretty much, so what's going to happen is, the way the circuit's going to work, we're going to take your audio input. It's going to come in. Now, small signals capacitors act like a short circuit to a small signal. So small signal's not going to care. Like Honey Badger, don't care.
Right. Exactly.
All right.
Exactly.
So what you have right here is the reason why we've got such large values in our resistors is we're trying to bias the circuit where this will function the way we want it to.
Right.
So what's going to happen here is you're going to have a voltage divider So we'll run you through a voltage divider real quick. So in order to do this, we're going to take our 12 volts DC. I'm hoping you can see this on this side of the board. And then we're going to multiply it by this value right here, which is 27K, plus the 27K, or divided by the 27K plus the 220K, and then that's going to give us our V1 voltage right here. Now the great thing about these circuits is they kind of they don't necessarily remove the DC component, but they don't amplify the DC component. All this is amplifying the AC component of our system, and the DC is only there to just turn everything on.
Right.
It's like the power company coming in and just turn on the lights while you do the work.
Exactly.
So that's essentially what's going on here.
Right.
So that's the reason why this side doesn't have a resistor, because we want to make sure that since we're tapping off the voltage of right here to come to our base, the only way to get this higher is to not actually have any resistance on there. In order for this transistor to now work, to get our audio output and our amplified signal to the speaker over here that you'll see is right here.
Right.
So then you're like, oh my God, how's this going to work? Well, essentially as your current comes in, you'll have of course your IE going this way. Well, it's actually your IC, part of your IC, this IC1, is actually going to go this way because this is essentially a parallel circuit. So we're actually going to have a part of IC. The overall IC right here, we're going to have each piece go this way.
Right.
And what's going to happen is it's going to, at this point, we've put a gain to it. In this section right here, we're kind of normalizing it, buffering it. There's each one of these two, they may look the same, but they're not. And each one of them has different functions within the amplifier, which is why we have two of them. And we'll go into that into some really detail. In your lab reports, you'll understand that this is a common emitter amplifier, and this one is also a common emitter amplifier as well.
Cascaded. Yeah.
You're right. And they're cascaded together to give us, I'm not going to say a clean signal, but it's going to be a really nice, it's going to be a nice signal. You'll be able to hear what's going to be coming out of it.
Yeah, of course.
So,
of course,
since we're not worried about polarity on these, on your simpler components, it's not a big deal which way you hook them up. It is a big deal if you look over here at Aspen Shoulder.
Here I am.
Yep. This is what the BJT is going to look like. You're going to have a flat side, then you're going to have a rounded off side.
Right.
And then, of course, we labeled it EBC for you, so that
looking at the flat side towards you. This pin that comes out of it is your emitter. The middle pin is your base, and then the pin on your right is your collector. Okay. Which is very important. Look going into onto the breadboard, because you want to make sure that you're not, reversing this. Keep this in mind, just because if you do hook it up incorrectly, and that's something that's very hard to notice sometimes. So your circuit might not work, or your output not going to be what it should be, and you're like, oh, why is this? What's going on? Just double check your components all the time, especially the more complex ones such as the BJT and how it looks. So
real quick, we're going to show you up close what your circuit's going to look like toward the end of the lab. And not to worry, we're going to guide you through this, so try not to flip out.
Of course.
You'll see the capacitors, you'll see the resistors. The resistors are these little guys like right here,
right,
and right there.
It's not as bad as it looks, I promise.
Nope. Make sure I'm touching the right thing. Then our capacitors are going to be these little round capped things with the silver tops. Those are the capacitors we're going to be giving to you. We know you may not have your training box at this point right now, so we're still going to run you through it. Want you to take notes. And then, of course, we will give you all kinds of detailed and awesome information inside your little lab manual, so that way you'll know what's going on. So, guys, we're going to shut it down. we're going to reset our equipment,
Right,
and then we're going to start building this thing.
All right,
Let's
we'll see
do it.
See you on the breadboard.
Okay, guys, welcome back. And so now we're going to go ahead and start building our circuit from what you saw on the board to now what you will see on your breadboard. So if you remember our circuit, well, if you look at your circuit there in your lab manual, you'll at least have your lab manual. Is we're going to start out real easy, and that's going to be coming from, this is going to be, we're going to start with our waveform generator. You'll make note that we have everything powered off right now. And again, if you remember everything we said in the safety video, that we're going to build this thing without any power to it. When you raise these things up, there is a small hole inside of the screw shaft. What you do right there is you take the little tip of your wiring right there, you put it inside that preformed hole, and then you go ahead and you tighten it down. It doesn't have to be gorilla tight, guys. We're not building rocket ships or anything like that here, so if you screw it way too tight, you're going to break it. So at this point, it's dealer's choice where you want to put it at. We're going to go ahead and give it a little push, and there we go. There is your very first connection.
Right.
So then our next stage is we go from our input. FYI, guys, if you can actually hear what's going on in the next lab over, some of our more intrepid classmates are actually working on a robot right now and using some rather large power tools to cut rather large chunks out of whatever it is they're cutting.
Right.
So if you hear a really loud noise, that's them working with power tools. Electrical engineers should probably never be given power tools, just FYI.
Well, just bear with the noise if you do hear it in the background.
Right. So then our next step, if you remember, is our input came in through a capacitor. So our first capacitor is we're looking at 0.47 microfarads. So the whole point of capacitors is they store energy. So that's what we're going to be doing right here. Is you'll see I'm connecting it onto the same row as our first wire. And there we go.
Right, because that is in a series connection. And a good rule of thumb to just know what's in series, what's in parallel is if you can follow the current, the same current through two different components, that means that they're in series. Okay, and as you see in your lab manual, that the capacitor follows right after our function generator. Okay, so they're both in series, and that's how we hooked it up on the breadboard, as you can see there.
Absolutely. Absolutely. All right. So then, if you remember from the board, you saw a green box around where our capacitor, our BJT, and two of our resistors met. So what we're going to do is we're going to connect from our voltage source resistor, which was 220k ohms, and you'll know how the resistors are by there is a resistance band on them. In this case, we're looking at a red, and yellow with a gold band. The gold band is just there to say plus or minus however percentage of tolerance it is within the resistor. So we're going to go here, we're going to take part of our power rail, and then we're going to connect it to the opposite end of our capacitor. And there we go. Well, of course, we had more than one connection on that. So our next resistor is a 27k ohm resistor. We don't actually have a 27k ohm resistor, but if you remember the video, our intro video talking about resistors, you'll know that when you put them in series, you add them up together. So that's essentially what we're going to do right here, is we're going to take two resistors. We have a 20k ohm and a 7k ohm. Or it was a 21k ohm and a 600 ohm resistor. I forget which one it was. But we're going to take these two little resistors right here. Note their resistor bands. So whatever you want to do, however you want to do it, just make sure you get up to 27k ohms. We're going to put one on our negative rail and then put it right by here on its own, because now what's going to happen from here is we're going to put our next resistor on that same row and then give us our 27k ohm into that node you saw, now going to ground. And then last and certainly not least is we're going to be putting our BJT in there. But since we're also going to make other connections from that BJT, what we're going to do is we're going to put us a nice little wire right here on that same row and then bring it out here away so we can now connect the BJT.
So notice just like before, this is the flat side facing you guys, right? So this is so this right here is our emitter, base in the middle here, and then our collector pin. Okay. So we definitely want our collector pin, that's right here to the right, to actually be where our 10K resistor is going to be connected also to our power strip, right? So what we'll do is that we'll also turn it around, okay? So now our collector is on the left side, base in the middle, and the emitter is on the right-hand side, okay? And actually our base is actually connected connected with that same node where the two resistors and the capacitor was. So we're just extending that out to here, okay? So we're going to put that right here. I hope you can see that clearly. It's just right behind on the same row as that wire connected in right there, right? Okay, and so now that you have here 10K, this is the 10K, correct, Brandon? Right?
Yes, it is.
Yes, it is. Okay, you see the color bands here. Similar, telling you this is 10K. And our 10K, if you remember, look at your lab manual, is coming from our 12-volt power source, okay, into our collector, okay. So how that's going to look is we're going to hook it up. We'll put it into right here. And by the way, guys, just a quick reminder, we're putting our resistors on this side of the strip, where the red line is, because this whole strip is powered up by 12 volts here. Okay, so wherever hole you insert a component is getting 12 volts into it. Okay, and then you see here, we're going to put that on the same row as our collector pin of our BJT. So now we have a 12 volt going to our resistor and then going into our collector pin of BJT. And now here what I'll do is I'll take our 1.5 kilo ohm resistor. Okay, so what happens is that we don't actually necessarily have a 1.5K resistor. So if you remember from our series in parallel video, we actually have two 3K ohm resistors in parallel with each other to give us a 1.5K resistance in total. Okay, that's going to work here. Going from our negative. Well, actually, let me. Parallel here. Kind of drawing a blank here. Okay.
Parallel.
Right.
So we're going to go from here. Also,
There we go.
to our emitter.
Of course.
And that's why we work in teams, because when someone forgets something, the other one will remember it.
Of course. Right.
So there we go with our 2 resistors now in parallel, giving us our 1.5.
And then lastly, for our first half of our circuit, essentially, if you remember, we also had a 4.7 microfarad capacitor in parallel with our 1.5K resistance as well. So what I'll just do here is on the same row as our emitter pin for our BJT. Hook it up here on this side. And then also hook that up to our negative, our grounded voltage strip. Okay. So with what we have set up now, this is just the first half of our circuit here. That's most of the nitty gritty, really.
Yeah.
Okay. It's pretty much smooth sailing from here on out, right? So continuing with our circuit, we'll actually take a watch such as this, right? So if you remember, if you look at it, we're now going from our collector pin to our base pin and our second, or our cascaded BJT here. So what I'll do is I'll connect this in the same row as our collector pin here in our BJT, just right there. I hope that's clear. We'll put it off to the side over here. Okay, as such. And so now what we'll do here is that we'll actually connect our second BJT. As you see here, the round side is facing you guys. So again, that means our collector pin is on the left, base pin is in the middle, and our emitter pin is on the right. Okay. And like I said, this is going to our base, so we'll hook that up right here on the same row as the wire is going from our first BJT's collector. And looking at the circuit, we now see that our collector pin from our second BJT is going straight to a 12 volt DC power source. So that means that I'll just same row as the collector with this wire here that has no resistance, obviously, virtually anyway. Straight to our power source strip right there. And then I'll take now our emitter pin going with a 1K resistance, which is easy enough, just 1K resistor right here, into our grounded power, into our grounded DC source, okay, to the ground, which is essentially 0 voltage. Okay. Now we also have a capacitor in parallel with that 1K resistor. So I'll open that. Let's see here, actually.
Make it easier on ourselves.
There you go. That'll work.
Bam.
Bam. And then we'll have one more capacitor. Our last capacitor is actually going from our collector, a collector part of our BJT to ground as well. So all that means is we'll just put this in the row of our collector. In parallel with our
We'll make it easy. If you remember if you remember our diagram real quick, it goes straight from the voltage. Remember that node?
correct.
So we can do that without problem.
Go, of course. And then if you remember that our speaker is actually in series with our capacitor here, coming from our emitter pin, which is here actually. So this is what I indicate. This is what we'll actually connect our speaker to in some sort here to this wire to complete our circuit. Oh, and then lastly, also, was Brandon point out to me that our speaker will be going to ground. Okay, so pretty much to finish it off, we'll have our speaker in series with this wire. Then also it'll be going to ground. Here as well. So definitely once you hook up your speaker, there will be. Bring the lines over here. These. Right, we'll make a connection, as you can see here.
Our alligator clips are missing at the moment, so it really doesn't hurt anything for you to take it and wrap it around the wire like you're doing.
Right.
We went ahead and spared no expense and got you guys some really nice capped off wires to make your lives a lot easier than trying to have to strip and how long is it.
Of course.
These are a little bit easier to break in the breadboard, but they're harder to break in the breadboard. I know that makes no sense whatsoever.
Right.
But if they're easier to move around and actually snap the little shaft off. But in order to snap that shaft off, you have to be intentionally moving this base around while it's plugged into the breadboard. And so now we have our last two connections right here, which is going to be our power connection, which we are going to connect to our little V plus right here, which actually, here we have our constant 12-volt source. And again, we're going to put that through the little shaft for the screw, that's what it's there for.
Of course.
And then, feels like something's pulling on the board. I've got a fish. And then, of course, we need our grounding component, which is what our ground is right here. Yay. And then that's going to give us the power we need to run this circuit. So, of course, guys, before you go ahead and power everything on, why don't you go ahead and have your instructor take a look at it. Make sure you did everything the way you're supposed to, because, like I said, once you turn this thing on and you release the magic smoke,
right,
that's
hard to fix.
As Porky Pig said, that's all, folks.
Right,
I mean,
exactly.
You're going to need a new component at that point. So right here, if you noticed on the board, we started out at 100 ohms, or I'm sorry, 100 hertz, which is our frequency. Right here, we're set on a sine wave, which is what we've got going. So we're going to go ahead and turn it on and see what glows, what blows up.
All right.
What hopefully goes right.
Mm-hmm.
All right, let's see here. No offset. So you hear the speaker? And you sit here and you can change the frequency.
Mm-hmm.
And you hear what happens. I don't know.
Right.
Try to get my microphone closer to it. That's 100 hertz.
Right.
And that's going to be just about 1 kilohertz right there. I'm going to show you by switching this from this top knob from 100 to 1000. So there you go. There's our bass. You may be interfering with the microphone at this point, but you still should be able to hear it.
Mm-hmm.
That's uncomfortable.
Right. Talk about a brown noise, huh?
Ow. Ow. And we can take this up to...
Okay.
We're going to take this up to 10 kilohertz. Oh, that's not fun.
And at this point, we might go out of the human's actually hearing range if it goes
we're
high
definitely
enough.
getting there.
Yeah.
But guys, there it is. So what we want y'all to do now at this point is why don't y'all go ahead and swap between these 3 tones. And y'all try to make some music, literally.
All right.
We're going to go ahead and shut it down because we're good on our end.
All right.
Hopefully y'all came out. Again, if something's not right, look back at your circuit in the lab manual and go through a piece at a time. Take it one step at a time. No one's in any rush.
Of course.
So let me go ahead and turn this off real quick before that gets annoying. You know, like Dumb and Dumber from way it's a little bit before your time.
I know.
You want to hear the most annoying noise in the world?
Right.
Yeah, we don't want that going on while we're doing that.
Right.
So, all right, guys, that's pretty much going to be the end of it. We want you to take a look at, you know, like we said, this is a real simple circuit, real easy to build, and it's a great audio amplifier. You get a gain, and I know we didn't really cover that much, so we're going to go ahead and look at the board real quick. All right. So our gain is, and we don't measure our gain from our DC component, we measure it from our AC component. So essentially our gain is our AV is equal to V out, our voltage output, our small signal voltage output over our VN. And that's how you measure gain. We'll go into some detail in our lab manual how to get this number. There's a lot of theory. I mean, there's a lot of theory, and we're just going to jump through the meat and potatoes of it and give you an overall understanding inside the actual lab report.
Right, of course.
But once you're there, you'll be able to see the gain. You'll be able to find the gain. And essentially, as each stage has its own gain, and you take that gain and put it into the next stage following. So since we've only got 2 stages, it'll be a real simple. You'll have a VI. Then you'll have a V1 or V1, and then that V1 will go into your next stage, and eventually you'll get your VO. So it's real simple.
Right. But at least now you know that the circuit can be built, and you've seen an example of it and how it should react and operate. Right. So definitely try to replicate the circuit here. And again, please just follow the steps correctly, and take your time with it as well. There's no rush. It's not a race. Okay, make sure that everything is in the right pinhole and stuff like that. And then have fun with it. Don't try to break it, but have fun with it at the same time.
Please don't break it.
Right.
Please don't break it. But guys, that's it.
Yeah,
I mean, of course, be safe. Anytime you have to make a change to the circuit, please shut the circuit off. Please do not make changes while power is applied. That could really go bad for you really quickly.
Right. So,
All right, guys. Thank you for staying with us through Video Experiment 1.
yeah.
Again, check your lab manuals for everything we didn't cover this time around, but I think
Right.
we covered enough to where you understand what's going on. The important part was building the circuit and then hearing the output. And we're hoping you're having fun with that. We're hoping you're annoying your teacher by now with all the awesome sounds you can make with a simple sine wave generator right now.
Right.
So that's going to wrap it up for video 1. Hope you guys have a great time.
Of
I know
course.
we had a great time with it.
Oh yeah, I love this.
So if y'all liked our video, go ahead and give us a thumbs up. Please subscribe to our channel. Leave us some good comments, constructive comments below.
Right.
We don't need anyone slamming us for our presentation or, be constructive, guys. If you got something bad to say, be constructive about it. Don't be a jerk about it. We'd appreciate that. And y'all have a great day, guys. And we will see y'all for video 2, which we will be shooting in about 5 minutes.
Right. Of course.
All right, guys.
Yeah.
Later.